Good morning, sir.
Hello, good morning.
Sir, the first session was prolonged by 10-15 minutes, so you had to wait for that.
Oh, it's okay. It's all part of the game.
Yes, yes. Just all the participants are getting joined.
Okay.
Because the session has just ended, so everybody will be joining.
Sure, no problem. No problem. You can see me clearly?
Sir, your video is off, I think.
Video is off. Okay, let me see.
Yes, sir. Yes, sir. So now it is.
Okay.
Yeah.
So today, how many participants are there approximately?
Approximately, sir, 125 they are there. But registration is of 200, but anyhow 20-30% absenteeism that remains.
That is always the problem.
Yes, sir.
No problem. So the first session was on what?
First session was on, sir, masonry structures, seismic analysis of masonry structures.
Okay.
So today is the second day. Yesterday we had the session on seismic controls.
Okay.
Then the buckling restraint braces.
Okay.
That was there. And one session was on pushover analysis.
Oh my God.
Yeah.
You have already done the advanced courses first.
Actually, sir, it's difficult to get the timing of the experts. So
Right. It's really very interesting. On one hand, we are talking about push-on analysis, controls, and on the other hand, people don't know how to carry out response spectrum analysis.
Yes, but sir, actually, 142 participants are the faculties, and 58 PG students are there. So I think all the audience that knows all the basics about earthquake engineering.
Okay. No, all right, but I'm just talking in general.
Yes.
I'm just talking in general.
Yeah.
That if you look at the results, you look at the design calculations of many people, you find there are, serious problems with the basics.
Yes, sir. So that's why such FDPs are very much helpful for all the audience, that they will get the thorough insight about all the basics.
In front of the other lectures, my lecture is going to be very, very elementary.
Sir, basically that is required actually. And I got the request from non-registered participants also that they wanted to attend your lecture specifically.
Okay.
Yeah. So I hope by the time the participant list will increase, it will be more than 130 or so.
It's okay.
Yeah.
It's important that the people who are interested, they should join.
Yes, sir. Sir, have you been in Gujarat in last days?
I was there just 2 months back.
Acha.
I was in Surat. In fact, I was in Silvassa.
Acha, huh?
There was a very big fire in the plant.
Okay.
It was it was theoretically it was a 5-story building, but otherwise it was a almost 10-story building.
Mm-hmm.
Because the story height was double.
Okay.
And the entire plant
Mm.
burnt for
Oh.
more than 18 hours.
Oh.
It was all chemical plant, and they had the huge finished product stored in the ground floor,
Mm-hmm.
and there was no access to go inside.
Oh.
The plant plan would be approximately 200 meters by 200 meters.
Okay.
All is a box,
Mm-hmm.
so you can go only on the outer periphery, not inside.
Okay.
And there was obviously they couldn't save anything.
Mm-hmm.
So this happened just 2 days before lockdown in March.
Oh. Mm-hmm. Okay.
So the problem was, how to get people there.
Right, right.
So our job was to find out, how much building can be retrieved.
Right. So whether it is serviceable or not now.
Yeah, it was in very bad shape. My God,
Oh.
horrible,
Mm-hmm.
horrible.
Fire is a big issue, sir. Actually, in Rajkot also, in one of the COVID hospital, it got fired and 6 people died in.
Yeah, yeah. I just saw the news 2 days back.
Yes, yes, sir. Yes, sir.
Yeah, yeah, yeah.
Mm-hmm.
The problem is that people don't take it seriously.
Yes, sir.
Neither
That is.
designers, neither
Mm.
designers nor owners, and then once the building is complete,
Mm.
they totally ignore the fire precautions.
Yes, sir. So,
We are seeing it repeatedly in every part of the country. You
mm.
remember a few years back, there was a big fire in Calcutta, a very prestigious hospital.
Yes, sir. Yes, sir. I remember.
Okay,
Yeah.
and many people died in that
Mm.
fire. It's really terrible. It's really terrible. And the fire is the worst way to die.
Yes, sir. Mm-hmm.
It's very painful, extremely painful.
So strong clauses are required in this case, sir. Yeah. So
See,
then
the
only
problem
people will get awareness about it.
problem is punishment. You have to punish.
Yes, sir.
You have to punish.
In major mass like us, that is what is the only solution, major punishment. Otherwise, people will not get
And we
that
have
much
somehow
serious.
such a soft corner. अरे जो मर गया सो मर गया इसको क्यों मार रहे हो
हाँ.
इसकी बीवी बच्चों का क्या होगा
Hmm.
that's the problem once you think on those lines then you can't do anything
Yes, sir.
with
So,
the fire which took place about 40 years ago in Delhi in that Upar cinema hall
yes.
today they didn't get the justice even today after 40 years
Hmm. So, sir, near to 90 participants are there. So, we may start, sir.
I think we should start here that's
Yes,
right
sir. Yes, sir. So, I'll just give the introduction and then we'll hand over to you, sir.
okay okay
Yes, sir. So, good morning, participants. So, now we have the much awaited session uh, that is there with us. Dr. A.K. Jain is there. Sir is retired professor in civil engineering in IIT Roorkee. He has obtained his bachelor's and master with honors from University of Roorkee in 1972 and 1974, and he has done his doctorate from University of Michigan in 1978. His main area of interest include multi-story buildings, concrete and steel bridges, nonlinear seismic response of the structures. Besides the teaching and research, Sir has been a structural consultant for various state and central government agencies, as well as many private companies. As you may have heard one of the case just before 2 minutes that Sir visited Surat in a burnt plant also. So The society is taking much benefit of his experience and expertise. Dr. Jain has published over 50 referred journal papers and over 60 conference papers in various topics, and Sir has authored 5 textbooks. The books are Dynamics of Structures with MATLAB Applications in Pearson, Reinforced Concrete Limit State Design. Now it's 7th edition. And I had just mentioned the sir when I contacted for first time that the fundamentals which I have learned through this book, they are still running in my veins. So it is so fundamental book, sir. So still I have in my library, sir. I have studied it before 22 years, but still the same book I am referring after 2 years, 22 years. So it's a very book, sir. Very good book, sir. Advanced
Thank you.
Structural Engineering with Finite Element Method, 3rd edition. Strength of Materials and Structural Analysis, 2nd edition, that is there. And Fortran Programming, 2nd edition in 1990. So still this details about sir is very short, but now I will request sir to just take over the charge over the session without wasting much time. So requesting sir to take over the charge, sir.
Okay.
Yes.
I hope you can see my slide now.
Yes, sir. Your slides are visible.
Okay. Well, I'm very thankful to the Marwari University, Dr. Tarak Vora, for giving me this opportunity to interact with you this morning. So today's my topic will be earthquake resistant design philosophy. In fact, Dr. Vora just told me that yesterday you had much advanced topics about nonlinear lasses, pushover lasses, etc. So as compared to that, this lecture is very, very fundamental. So I'm talking about the earthquake design philosophy today. So earthquakes are of different types. They occur due to different reasons. This is a volcanic earthquake, which also causes a lot of damage to the buildings. But we are talking about here structural earthquakes, which cause due to the movement of the Earth's plate within the Earth's uh, tummy, and a lot of energy is released, which results in shaking of buildings in the lateral direction mostly, and cause tremendous damage. Now the question arises, how do we carry out the design of buildings to resist the earthquakes? We can't, of course, we can't stop the earthquake from occurring, but we can certainly take precautions so that our buildings remain safe and the people who are inside the building are also safe. So there are essentially two types of design philosophy. One is the prescriptive design, which we have been following for the last several decades, and the new philosophy, which is called performance-based design. Now, these two philosophies are uh, two opposite poles, North Pole and South Pole. In a performance-based design, the code is supposed to only specify what is an acceptable level of protection against structural failure under extreme load. Now, how to do it is to be totally designed to be taken care of by the designer. Okay. In a case of prescriptive design, the code specifies what to do and what not to do. Okay. For example, what should be minimum size of the column, what should be the minimum size of the beam, what is going to be the minimum reinforcement in a column, what is going to be the maximum reinforcement, minimum spacing of reinforcement, maximum spacing of reinforcement, and so on. So everything is prescriptive. It specifies what exactly you have to do, what you are not supposed to do. Okay. The problem with the prescriptive design is it may be either oversafe or sometimes it may be undersafe also. But you have more responsibility because you are following the code, and this is what the code says: do this, do this, do this, and don't do this, don't do this, don't do this. So the entire responsibility lies with the code in this case. But it's not really a very logical or a rational design technique. It's better that code only specifies minimum requirements that we want, that this should how the building should perform in a given situation. And then the designer should be able to put all the parameters together and come up with a design. Of course, in that case, the level of maturity and experience of the designer has to be of the highest order. Now, why do we go for a prescriptive design? It is because it is simple to design and simple to check. Okay, because everybody knows what are the prescriptions. Then simple can be economical and no need to reinvent the wheel on every new project because everything is well defined. What is the problem with the prescriptive design? The problem is it leads to loss of rationale and loss of ability to improve upon it. Loss of innovation leads to loss of economy, and loss of rationale can also lead to loss of compliance. Because nowadays, especially if you look at the current IS 1893 earthquake code, part 1, as well as 13920, there are many clauses which are very difficult to understand, very difficult to follow, and therefore there is a loss of compliance. Okay, so people have developed their own understanding. Okay, we'll do like this, and they go ahead with it, and it is approved, knowing fully well that it does not really comply with these codal requirements. But what to do? If the codal clauses are irrational, you have no option. Now, performance-based codes. ASIA 318 code and the Eurocode 2 is quite close to performance-based code, but not exactly. Now, what is involved in a performance-based code? There are three parameters which you have to understand. One is the performance index. The code is supposed to specify a performance index and then how to verify the performance and how to evaluate the performance. So these are the issues. That's why the performance-based codes are not fully available even today. They are in the conceptual stage, quite advanced, but not fully available so that people can use it in the real sense. In a performance-based code, it is important that the possessed performance of the building should be more than the required performance of the building. Okay, it's called required performance index PIR and possessed performance index PIP. For example, the possessed performance index denotes what is the seismic capacity of a structure. Okay, and the required performance index denotes what is the seismic demand of a structure. Performance items: comfortable ride, walk, comfortable stay, anti-vibrations, anti-noise, anti-odor, anti-humidity, and on the right hand side in this table, I have shown performance indices. For a comfortable ride or a walk, acceleration, natural period of the structure component has to be under control. For comfortable stay, lateral deformations or the story drift should be under control. Similarly, all the parameters are specified. Now there is another limit state called damage control limit state. In a damage control limit state, damages to plastic hinges and members are within the repairable limit. Non-hinge members do not yield and members do not fail in shear. If you don't want a brittle failure, everybody knows that a shear failure is a brittle failure. Okay, so we don't want shear failure. We want that the failure should be a flexure failure, And the members are not supposed to develop plastic hinge. That is, non-hinge members, they should not yield. That means they should remain elastic throughout. What is wrong with the performance standards? Quantitative criteria, sometimes difficult to develop, often difficult to achieve consensus. If there are two different designers talking about the performance standards, they may have their two different views. Then evaluation, how to evaluate the performance? That is the biggest question. Measurement is the key. How to measure the performance? It is essential to find a way to measure analytically or experimentally a meaningful quantity. What is the design criteria? The design criteria is the structure must be able to resist all expected and probable loads on the structure safely during its entire design life. Various loads I have specified here and the combinations. The present approach is carry out elastic analysis and magnify the member forces by partial safety factors to get the forces at collapse. So you calculate, you carry out elastic analysis and get the bending moment, shear force, etc. And from there you get the factor bending moment, factor shear force by multiplying by some load factor 1.5 or 1.2 or something else. Okay. What it means physically? It means physically that the entire building is going to plastify simultaneously. Okay, because you are taking the entire building to plastic hinge by a single factor 1.5 or 1.2. So it means simultaneous plastic hinging in the entire structure, which is a highly improbable situation. That is the flaw with it. Now, if you take a building, subject it to lateral loads, you have already done push-over analysis yesterday. So I believe you must have understood the particular diagram. What it shows is that when you start the loading from zero and keep on increasing slowly, monotonically, okay, then at certain location, hinge will form. Say in this case, the first hinge will be a plastic hinge in the red color, okay, and hinge will form. Then the yellow color shows the next hinge. It shows in this force deformation diagram where is the hinge that is forming, okay, and then the blue hinge, white, and so on. So you see in the diagram on the building that all the hinges do not develop simultaneously in the entire building, in every bay, in every column. Okay, some hinges form first, some hinges form later, and the hinge which form first will keep on deforming, continue to deform because the loading is continuously increasing. Okay, that is the real situation of this lateral load application on a building. Whereas what the code is saying, code says that you take the elastic forces and multiply certain factors. That means all the hinges in the entire building, red color and yellow color, they form simultaneously. Okay, and then the building may collapse or building may remain elastic depending upon what is the level of the lateral forces. Okay. Now this is what it shows the distributed versus simultaneous hinging in a building. Force deformation relationship. The lower curve shows simultaneous formation of the plastic hinge. That means it will fail earlier because all hinges are formed together. But if you take the distributed plastic hinge sequence, then the building will take much more load, much more deformation, and it's quite possible it will not collapse. Okay, so that is the advantage of this building. The problem is that to tell the common designer or an average designer how to do this distributed plastic hinging, for which he has to carry out a non-linear analysis, that would be very, very difficult because of the average, the maturity of the average designer is not that much, not only in India, but even in Western countries like Europe and America. So it is a universal problem right now, and that's why everybody is following the simultaneous hinging approach rather than the distributed plastic hinging approach. Now let us revert back to the prescriptive design using the conventional limit state design philosophy as specified in our IS 4, 5, 6 code. Okay. Now let's look at the design for earthquake resistance. Now what is the design philosophy? The design philosophy is we try to divide the earthquakes qualitatively in three categories: minor earthquake, moderate earthquake, and a severe earthquake. We say that in a minor earthquake, non-structural damage will occur to the building. In a moderate earthquake, which may be in once in 20 years or 30 years, only there may be minor structural damage which can be easily repaired. And severe earthquakes will occur once in the lifetime of the building, maybe once in 100 years, maybe in 200 years, and there may be a major damage, but the building frame should not collapse. The intention here is that let there be damage to the building, so we don't care about the building, but we do care about the people who are occupied inside the building, and they should come out safely. Okay, so that is the design philosophy for the earthquake resistant design. Now, those who have seen the latest code 2016, they have removed this design philosophy from the preface. I don't agree with this, why they have removed it. I don't know why they have removed it, but they shouldn't have done it because this is still widely accepted worldwide design philosophy for earthquake resistant design. So as I said, there are three kinds of earthquakes qualitatively: small, moderate, and large. In the small earthquake, what is the controlling factor? The controlling factor is deflections by providing enough stiffness in the building. In a moderate earthquake, where there can be only minor structural damage, the controlling parameter is strength of the members. In a large catastrophic earthquake, where we want that there should not be any collapse in the building, which could cause loss of life, allow structure to enter into elastic range and absorb energy by providing ductility. So in a small earthquake, the controlling parameter is stiffness. In a moderate earthquake, the controlling parameter is strength, and in the large earthquake, the controlling parameter is ductility. Please give me a moment. I will just be back in a second. Okay, I need to bring my mouse. Sorry for that. I'm sorry. Actually, so this is stiffness, this is strength, and this is ductility. The last half century has seen evolution of very effective theoretical and practical steps for minimizing losses in earthquakes. However, the losses continue to be extremely high in India because of ignorance and socio-economic conditions. What does it mean? Let me show you. The maximum losses are in remote areas of the country where traditional stone masonry and poor construction practices are prevalent. These are some of the major earthquakes that have occurred in the last 40-50 years. That is the Kinnaur earthquake in Himachal Pradesh in 1975, then Uttarkashi earthquake in 1991 in the hills of Himalayas, and Latu Tewari earthquake in 1993 in Maharashtra, Bhuj 2001 in Gujarat, and Pak occupied Kashmir, that is Islamabad, in 2005. These are some of the major earthquakes which occurred in the last 50 years. In the past, in hilly areas, timber or bamboo framed buildings were built, minimizing the losses. That was the past practice developed by our ancestors. Okay. However, deforestation and socio-economic factors change the building materials and design practices, construction practices, leading to greater losses. Now, everybody wants a pakka house. Okay. They think that if somebody living in a timber house is a very poor person, a bamboo house, very poor person, he doesn't get the social aspect. Therefore, he is forced to switch over to masonry buildings or RCC buildings, which are very much vulnerable to earthquake rather than these lightweight buildings. This is a photograph from Kathmandu Palace in Nepal. This is more than 300 years old palace building, and you can see here this is the timber band all around this courtyard, and they have windows, big windows, and with these big lintels. Okay, we see that they had some idea that they have to provide a band, a wooden band, all around so that you get continuity and the building remains safe during an earthquake. This is a building in Baramulla in Kashmir, and you can see here it's a very old building, more than 100 years old, and they have used timber bands in the at the floor level. Then you can see these bands here. Okay, and that's what our courts are saying, they provide the bands. So our ancestors knew that they have to provide bands in masonry, timber bands, so that our building remains compact and a strong entity during an earthquake. They have provided beautiful truss, wooden trusses with all the members interconnected so that during earthquake it will remain safe. This photograph is again taken from Baramulla. Now you can see our latest buildings, or huts you can say, in hills. This is a stone masonry, and there is no bond. They are not using even mortar because they are so poor. They can't afford to put mortar in these stone pieces. And look at the roof. Roof is built of slate. It's a very heavy material, and if during an earthquake occurs, because there is no bond, so these walls will fail. They will collapse. And what happens to the roof? It will fall on the people who are inside the hut. And that is the reason, because of the lack of bond and lack of interlocking, when there is an earthquake in hills, you always read that there is a lot of casualty. That is the reason. And these are the buildings which are causing that casualty. Okay. This is a building in Pokhara, which is a very famous tourist spot in Nepal. And you can see it's actually a hotel building, and there is a tapered roof for the rear side, front side, and you see here this thing. So this junction here is a very bad junction from the point of view of earthquake. So it's a masonry building, stone masonry of course, and this junction is very bad because in the case of lateral shaking, this will hit this wall, and this building is going to collapse. So architecturally it may look beautiful, but structurally it is a very, very bad design, and moreover you have stone masonry without bands. Let us look at some of the typical damages during earthquakes all over the world. Of course, this is soft story failure, and I'm sure everybody from Gujarat is familiar with this particular building. This is a two-story hospital building in San Fernando, California, which failed during a San Fernando earthquake in 1971. See, this is supposed to be the ground level, this is supposed to be the road level, and this building has sunk by one floor. And the entire building has sunk by one floor. This was the first floor, which has gone down. Okay, and so this was the open story. This is the elevation of this same open story. So this frame has gone down, and you can see here somehow by accident this column happened to have a tight column. Okay, and the inner column happened to have a spiral column. There is no reason why this was made a spiral column and this was made a tied column with lateral ties. Okay, but what happened during this earthquake, this tight column is badly damaged, whereas this column with spiral reinforcement is intact. So in a single building, this is a very beautiful slide which shows that the behavior of a spiral column is very good during an earthquake as compared to that of a tied column. This is a failure of in a building in 1999 in Taiwan. Okay, the soft story failure. This building collapsed on the adjoining building. So the adjoining building was all right, but because of the earthquake, soft story, this building collapsed on the other building. So both the buildings are gone. The another building from same earthquake in Taiwan 1999, I can see here in the middle bay here, all the beams have failed. It is a beam column joint failure. Okay, otherwise the whole building is intact. But because of this beam column joint failure, the entire building is gone. It has to be demolished. Then torsion in buildings is a single factor which is responsible of collapse of almost 90% buildings all over the world. Okay, and torsion means that means our building is irregular. If you look at the classification given in IS 1893 Part 1, all those buildings which are irregular buildings, either in plan or elevation or both, they introduce torsion in the building and they are responsible for the collapse. How they are responsible? See, the purpose of the torsion is to increase the forces in the building, and the increase in the lateral force is not much. It's about 15 to 20% only. So what most people are doing, because the architect wants an unsymmetrical building, so they say, okay, you go ahead with the unsymmetrical building or irregular building, and I will provide the additional forces of the 20% or 25%, and now I think that the building will be safe. Now, that's a very, very wrong concept. Because in torsion, the increase in lateral force is not critical. What is critical is the increase in the deformations. Okay, in deformations in concrete. So you have concrete columns everywhere, the concrete beams everywhere, and because of the torsion, there is an increase in lateral strain in the columns and beams, and concrete cannot bear that kind of strain. Once the strain exceeds the permissible limit in concrete, which is um, um, how much? 0.7%? No, more than that. So as soon as that limit is exceeded, the building will collapse. So very difficult to sustain these high deformations. That's why there is a collapse. This is again a building from Gujarat, Ahmedabad, and you can see here, or Ahmedabad of Bhuj, and you can see here that only the lift core remains and everything has gone down. This is because of this torsion in the building. This is sorry, Mansi Tower, the adjoining block collapsed, and look at what happened to the staircase. Again, torsion and soft story in this particular building from Gujarat earthquake. Same building again. You can see clearly there is a torsional mode. What happens that every time there is an earthquake, there is an outcry to upgrade seismic zone. This is what happened after this Gujarat earthquake. Zone 2 in Bombay was increased to zone 3, and zone 1 was increased to zone 2. Okay, there was no logic why these zones should have been increased. Upgrading the zone means enormous additional cost and pressure on the precious resources of the country. Okay, and this doesn't solve the problem because the problem lies somewhere else, and there was no need to upgrade the zones. Upgrading the zone is not a solution. What is the solution? The solution is better planning, appropriate material, workmanship, and detailing. That's what is required. That means more pressure on the designer so that they are more careful in how to design this building. The key is to provide continuity, redundancy, and ductility in the building. General principles of earthquake resistance, you know, lightness, configuration, that is symmetry in plan elevation, uniform strength in various directions, continuity of construction, redundancy, and seismic resistance elements at the perimeters. You have to provide ductility so that you have got reserved energy in the structure. Projections and suspended parts should be minimized because they reduce vulnerability to vertical accelerations. You have to be careful about the non-structural elements and foundation which should be interconnected. Use raft foundation or piles and make sure that you have the tie beam connecting all the pile caps. So what is the objective of IS 1893 code? To provide lateral forces to earthquake depending upon seismicity of the area, characteristics of the structural system, materials, etc. If you look at the earthquake code, 1893, the first code came in 1962 and then revised and like this, and then the last code was revised in 2016. It is in 5 parts. You know all the 5 parts. This is seismic zone 2002. Slight changes in 2016 map. Now, how to analyze the building? Seismic cohesion method, called study method, response spectrum method, a dynamic analysis or modal analysis, and time history analysis method is the third one. Okay, we are mostly using either one or two, but time history method is still not there in the IS 1893 code. And that's where I have a problem with the pushover analysis as well as other non-linear time history analysis, that if the code even today is not able to specify how to carry out linear elastic time history analysis, and they have not incorporated it fully in our IS 1893 code. So, but now they are talking about this pushover analysis or other nonlinear methods or these energy absorbing techniques. So I don't know how they go together. The question arises, out of these three analyses, which should I carry out? The answer depends upon what performance level you are going to achieve, the configuration of the structure, how accurate you need to be, and a wide range of choices are available. It is a single equilibrium system. If today we reduce our multi-story building as an equivalent single degree equilibrium system, this is a portal frame related to lateral displacement. This is another mathematical model. There is a mass, temper, stiffness, and this is supposed to be resting on frictionless wheels so that it can move back and forth. This is approximate modeling, and this is the equation of motion. ms double dot plus ks dot plus k is equal to minus my double dot, where y double dot is the ground acceleration. Okay, so the response of a single equilibrium system having given natural period of vibration or natural frequency and viscous damping, and we need to calculate what is the absolute maximum displacement, velocity or acceleration when subjected to a given ground acceleration. This is El Centro earthquake 1940 hexagram of May. Now, what is El Centro? El Centro is a very small village in the state of California in USA, which was the first place to record the strongest earthquake ever recorded in those days. And that's why this has a very historical significance. And the maximum ground acceleration here you can see was 0.33 g. Okay, if you remember in Koina earthquake, the maximum ground acceleration was 0.67 g. Still, the Koina earthquake stands nowhere as compared to this particular earthquake. This is a very, very damaging earthquake. It caused tremendous loss of property in 1940 in the state of California. By carrying out a single equilibrium system analysis, you can get the spectral acceleration for different dampings. The bottom one is 0% damping, 2% damping, 5%, 10%, and 20%. 20% is supposed to be very, very high damping, and that's how this structure behaves. Now, these are response spectra given in our code in 2002. The lowest curve is corresponding to hard soil, and the top curve is corresponding to the soft soil. That means for a given period of vibration, 1.5 seconds, this hard soil gives you minimum acceleration, whereas a soft soil gives a much higher acceleration. Okay, in 2016 code, they have given, they modified this small curve here, which in my opinion was not required, unnecessarily making it complicated. And they have this response spectra, and they also increased from 4 seconds to 6 seconds or 8 seconds, which was again not required. There are two terms which are important here. One is the maximum conserved earthquake called MCE. Now, this term was introduced back in the Uniform Building Code in 1997 in USA, and it was defined as an earthquake having a 10% probability of accident in 100 years. Okay, that's how it was defined in the UBC code. And again, in the UBC code, DBE, design basis earthquake, was defined as a 10% probability of being accident in 50 years. Okay, that's how it was defined there. Now, these two terms were borrowed from the UBC code in the Indian code, but they changed the definitions. They simply said, instead of making them based on probability, this probability here and this probability here, they ignored the probability terms. They said that this is DB is a moderate earthquake, may cause minor structural damage, and MC is a severe earthquake, which cause severe structural damage but not collapse. Okay, so these are purely empirical definitions. But in 2016 edition, unfortunately, even these two terms, DBE and MCE, have been deleted. Okay, there was no reason to delete them. I think they should bring it back because that is the basis of the whole response spectrum. See, this response spectrum which you see here, this is applicable at MCE. And when you divide it by 2, Z by 2, then it becomes DBE. Okay, so since you are still using the same formula for the base shear, that is F H is Z by 2, I by R, SA by G. So this 2 reduces this spectra or this acceleration at MCE to dB. Okay, Z is zone factor, I is the importance factor, R is the response reduction factor, which varies from 1.5 to 5, and SA by G is the spectral acceleration. Okay, and here base shear is alpha H times W times xi. Xi is damping factor. So for 5% damping, this factor is 1. For other damping, the base shear is supposed to change. Okay, and again in this 2016 edition, which I find 2 step back. This 2016 earthquake is stepping 2 step back than 2002 earthquake spectra of this code. Okay, so they have removed again xi, which is not logical. Now response reduction factor R is equal to 1 means it is a brittle failure, and R is equal to 5 means highly ductile behavior. It accounts for ductility, it accounts for overstrength in a building, it also accounts for redundancy in the building. So R is a combination of these 3 factors taken together. The value of R and I are specified in the individual parts of the 193 code. For example, part 2, which is dealing with water tanks, it defines what is the R value for different types of water tanks. Okay. Similarly, for industrial buildings, is part 4, which defines how to take R for different kinds of buildings. Okay. So these are the consequences. Calibration of the earthquake force in the old and new earthquake. I will skip this part. Now, where is the point of application of the earthquake force? You have a building, so at what point the earthquake force acts on the building? Okay, the earthquake force acts through the center of mass at each floor. Okay, so you have a static force you apply through the center of mass at each floor. The eccentricity of the applied force is given by the following equations given in the earthquake code. There are 2 set of equations, EDA and EDB. ED means design eccentricity. So design eccentricity A and design eccentricity B. The formula for A is 1.5 times E plus 0.05 B, and other one is E minus 0.05 B. So what is the physical significance of these 2 equations? In a building, on any floor, one side may be more rigid as compared to the other side. Okay, so we say the rigid side and so equation 1 governs rigid side of the building, whereas equation 2 governs flexible side of the building. What does it mean actually? How does it govern? Let's understand what is E. E is the eccentricity between the center of rigidity and center of mass at each floor. CR is center of rigidity and Cm is center of mass. There is another definition of eccentricity. It is the eccentricity between the shear center and cumulative center of mass at each story. And what is B? B is the width right angle to the direction of the earthquake, width of the building. Okay. The factor 1.5 here, this factor 1.5 and the factor 0.05. So factor 1.5 represents dynamic amplification factor and the factor 0.05 represents extent of accidental eccentricity. Okay, I hope this part is very clear. Now look at this particular diagram. This is a plan of a building. This is the rigid side. Okay, this is the center of rigidity is here, and this is the center of mass, and earthquake force will act through the center of mass. The width of the building is B, which is rectangles to the direction of the earthquake. This is a plan of the building. The rigid side, center of rigidity is here, and center of mass is here. And the distance between center of rigidity and center of mass is E. Okay? And when the earthquake acts in the y direction, in this direction here, then again you can see what is the, you act through center of mass. So center of mass and center of rigidity will not change. Okay? So this becomes the eccentricity in that case. So this diagram shows the basic definition of eccentricity. I hope this part is clear. So CR is toward the right. That's why this side is the rigid side. Now what this first equation is saying, that the design eccentricity is 1.5 times E plus 0.05 P. Okay, so you have this E between center of mass and center of rigidity. You increase this by 1.5 factor and add 0.05 B. So that means the distance between center of rigidity and center of mass. So this is the modified center of mass. And this becomes total EDA as given by this equation number 1. So physically, it means this, that your center of rigidity here, your original center of mass is here as before, but this is the modified center of mass which goes at a distance of EDA. Okay, so you design the building for this eccentricity and calculate the forces and check the building. In second case, you have center of mass here, center of rigidity is here, and EDB becomes E minus 0.05 B. So this is total E from here to here. Out of this E, you subtract 0.05 B. This distance is 0.05 B. This becomes eccentricity B, second definition. Okay, this is the modified center of mass, and this becomes EDB. That is the physical meaning of this second equation. Now what happens when the building, when there is earthquake and the building is unsymmetric, that is, there is an eccentricity between center of mass and center of rigidity. This is the action. The active force acts through center of mass, and this is the reaction. The reaction passes through the center of rigidity. So the building will resist this earthquake force by acting equal and opposite force through the center of rigidity. And the distance between this action and this reaction, okay, this gives you torsion in the vertical plane. Vertical axis in the horizontal plane. Okay, so what will happen? This is a flexible side, this is a rigid side. So this building will rotate like this. So there is a column below it. So the column will have to extend by so much. This column will have to extend by so much. And the question arises, is it possible that your column, concrete, can take so much of resistance? Okay, so much increased strength can the concrete take. If concrete can take this much additional strain, your building will be safe, otherwise the building will collapse immediately. Okay, so the building rotates about the center of rigidity, and that's what happens here. Okay, now somebody raised a hand. Now should we take the questions in between or should we take the questions at the end?
Generally we take it at the end, but it is up to you, sir, if you want to allow.
I think let's go up to the end, otherwise.
Yes sir, that's right.
Okay,
Okay.
thank you. Thank
Yeah,
you.
जी sir.
Now the point is, if you have designed your building for earthquake, you've done all kind of analysis, time history, pushover analysis. You provide passive energy absorbing devices in the building or active energy device in the building. The question arises: what is the guarantee? Can the designer give a guarantee that now my building is 100% safe against earthquake? Okay, the answer is no. I don't think there is any designer on the earth who can say that yes, the building is 100% guaranteed. Okay, but what happens when the building collapses? You can see these cracks here. So the designer is here. This is the designer. He says, I followed all the guidelines. I don't know why the building has failed. I should talk to my attorney, my lawyer. Okay, and he is the owner. He says, you designed a building, and the building was supposed to provide immediate occupancy. What happened? Why the building collapsed? The first earthquake itself. How could this happen? The loading that will occur in the future is uncertain. Actual strength of materials and quality of construction is variable. Neither the real demands nor the capacity of the structure to resist these demands can be perfectly defined or accurately defined. Earthquake force is highly unpredictable, unknown force due to lack of data. Earthquake depends on magnitude of earthquake, frequency content, duration of the earthquake, and peak ground acceleration. Now let's look at the detailing of the reinforcement aspect. So what is the philosophy of detailing of reinforcement? Ductile failure, that is structure failure, is desirable. See, out of the two failures, we have divided the failure in two categories: shear failure and structure failure. So we say that the shear failure is a brittle failure. It fails suddenly. It doesn't give us any warning, and therefore it must be avoided. Another failure is the structure failure, which is preferred, although we don't want any failure of any kind at all. But if at all there has to be a failure, then I would say that let it be flexure rather than shear. So it is a ductile failure, which is ductile, it is desirable. Why it is desirable? Because this will give me warning, sufficient warning to take corrective actions in the building. What is the option of the designer? Depend heavily on the reserve strength, that is nonlinear energy, that is ductility. For that, I have to consult 13920-2016 code. Okay, let me give you a conceptual idea about ductility. What is ductility actually? Suppose this is a true force. This is force and this is deformation. This is a true force. I know that the building will resist this force. So if I design my building for a higher force than this true force, okay, that means the building will remain elastic throughout. No matter what is the magnitude of the earthquake, this building will remain elastic because I have designed this force building for a much higher force than the true force that I can expect during a earthquake. Okay. Now it only means that it may become very expensive because I am designing my building for the maximum possible earthquake force in its life, which may occur, which may not occur. I am designing for a higher force. Okay, that means I am increasing my cost at the so-called advantage that it won't fail. It will remain elastic float. Okay. Now, if I want to make it economical, what I can do is I can design it for this force, okay, instead of this force or this force. So if I design for this force, I know very well that tomorrow this level of force or slightly more than this force can occur. So once I'm designing for a smaller force than the true force, it means the only way my building will remain safe without collapse will be that it has to enter into the inelastic region, force yield region. Okay, and if I want to be even more economical, I still design for a still lower force, elastic 2. So instead of this force level, I design my building for much lower level of force and rely on ductility. Okay. I hope this point is clear to everybody. And that is the meaning of R factor. This here R is equal to 1. Here also R is equal to 1. Here you can say maybe R is equal to 3, for example, and here R may be 5. So I am reducing my force, my true force, by factor 3 here or by factor 5 here. Okay, so that's now should be understood to you why it is important to choose R factor very carefully. And then once you choose R factor, you should know that you have bought a insurance policy that your structure will have to undergo inelastic deformations. Okay. Now, ductility is the capacity to deform. How to deform? How to define deformation? It may be curvature ductility, it may be a rotational ductility, it may be a displacement ductility. Okay? So curvature ductility, rotational ductility, and displacement ductility. Now these have different meanings, their values are also quite different. When we say a displacement ductility of 5 or 3, R factor 5 or 3, it essentially means we're talking about displacement ductility. Okay? I have carried out a lot of nonlinear analysis in the buildings, and I find that even it is difficult to achieve a displacement ductility even 3. Okay? Because the structure fails, it collapses. So you have force for displacement relationship. Okay? And this is the yield point. Okay? And this is the maximum displacement ductility here. So displacement ductility is defined as the ratio of maximum displacement caused in the building without causing any other serious collapse to the yield level displacement. Okay, this ratio is known as displacement ductility, and it depends on the structural properties of the building. Okay. Now this is a very beautiful diagram, a photograph in fact, of a building which was taken from a earthquake which occurred in 1964 somewhere in South America. Okay, in those days we were using M15 concrete and we were also using mild steel reinforcement Fe250. Okay, and you can see here this beam or this portal frame, it has sagged so much at the middle. Okay, and you can see here there is a vertical crack at the middle span. And you know what is the meaning of the vertical crack? The meaning of the vertical crack is that it is a flexure crack. That means this crack has occurred because of the plastification in bending. And you can see here the entire half span, there is no diagonal crack. Okay, there is no diagonal crack. That means this beam did not fail in shear. And this photograph was taken sometime in 1964. Okay, that means in those days nobody had any idea what is nonlinear analysis, what is ductility, and what is these push-over analysis, etc. Okay, so and it is not even clear whether the building was ever designed for any earthquake code in those days. So this gives us a very, very important lesson that first of all, our building is not a slave of any code. Similarly, even the designer is not a slave to the code. Code is different, but the understanding of the designer is totally different. Okay, so the understanding, the selection of proper materials, proper workmanship, proper detailing of reinforcement is the most important thing. Let us not become too much slave to the code, and that's why I'm saying that our code is becoming very conservative day by day. In fact, if I may use a term, both our codes 1893 from 2016 onwards and 13920 again 2016 onwards have entered into what I call as a panic mode. Okay, why I'm calling it panic mode? Because the level of force is increased drastically, the reinforcement is increased drastically, the size of the members increased drastically, and there is evidence. What evidence do we have to increase these forces so drastically? I don't see any evidence. Okay. Whenever I talk to the people who are involved in the framing of the code, they have no answer for these questions. Okay. They are not able to provide a commentary to their specifications. What is the basis for removing this MCE and DB in our code, where they are still derived from the same basic definitions? Okay, why should they increase the reinforcement requirement? Why should they increase the size of the columns? For example, nowadays the width of the column has to be 20 times the bar diameter. Even all internal columns have to have width of the column 20 times the bar diameter. From where they got this specification? They borrowed it from ACI, but modified it and applied everywhere. It was not the intention in the ACI code. So they have entered into a panic mode. They don't have much experience of designing buildings. And now what is happening? That there is a problem with the compliance. Many designers are not complying with those specifications. Okay. So what is the point of having a code if it is not being complied properly, or if it cannot be complied in view of these arbitrary imposition of the clauses in the code? And that's why I like this particular building. It was not designed for any code. There was no plastification requirement or codal ductility requirement in the clause in the code in those days. They use M15 concrete. This whole building is built up of M15 concrete and mild steel. And today we have so many high grades, M30, M40, M60, FE500, FE600, and still our buildings are collapsing. In India, if you see, almost one building is collapsed somewhere in the country, maybe Delhi. Okay, there are so many cases are happening reported on TV almost every day. In spite of so much advancement, so much material technology advancement, so much computer models, and so on. We are supposed to refer these codes for the detailed detailing, and don't forget this IS 456 code, which has to be followed. So you have to satisfy all these requirements, this code, and this code. Now, what is the idea of detailing of reinforcement in different elements? The idea is to provide confinement of reinforcement. Okay, because in the concrete is in a triaxial situation, that is, it is being confined from all directions. There is increase in its ultimate strain or the failure strain. That's called capacity design. The capacity design, you have to identify what are the probable locations of plastic hinge in all the structural elements. Okay, and then you make sure that the hinge will form only at that location and not anywhere else. That's the whole purpose of capacity design. So you identify the probable locations of plastic hinges. And how do you define the probable location of plastic hinges? You have to carry out a nonlinear analysis. Now, when you carry out nonlinear analysis, the problem is how do you model your beam? How do you model your column? How do you model the beam column junction? How do you model the steel? How do you model the reinforcement and so on? How do you model the shear reinforcement? Now, those are these questions which are still not answered. So it is very easy to talk about capacity design. It is very easy to talk about pushover analysis, but there are problems. There are serious issues involved. How to model a building for non-linear analysis. Okay, and then once you carry out a time history analysis, then how to carry out time history analysis? Which time history? Where is the data? If you remember, this Bhuj earthquake which occurred in 2001 in Bhuj, it was not recorded by such engineers. We don't have the infragram of this earthquake, except there was one building which was completed on 26 January. In fact, 26 January 2001 in Ahmedabad, there was the passport of his building. And these people installed one exogram in this first floor. That is the only available exogram available of that particular earthquake. Okay, but even that is not widely circulated to anybody. Okay, we don't know who has a copy of it. That means even the Bhuj earthquake was not recorded. And after that, there is not a single strong earthquake occurred anywhere in the country. Okay, the question is, if we don't have recording of those strong earthquakes, we do have recordings of the earthquakes occurring in Assam, Arunachal Pradesh, Meghalaya, and so on, but those are very, very minor earthquakes. Okay, similarly, we do have earthquake recordings in the Himalayas, but none for the strongest earthquakes so far. Okay, if we don't have a time history recording of a real earthquake in India, which is a strong earthquake, so how should we? Why should we talk about on what basis should we talk about nonlinear analysis or Pushmo analysis? Okay, that means the earthquake hazard in India is much lower than what is made out to be. So we'll discuss this little more in the subsequent slides. A knowledge of the plastic hinge theory is required to understand and appreciate the concept of plastic hinges. And as I said, here the biggest issue is how to model a building for nonlinear analysis. Okay, and that is still open to question. There are several models which are available, and there are several thinkings. Everybody comes up with a different model, and you change the model slightly, and the results are totally different. Okay, so if you change the input parameter slightly, and your results are totally different, then how do you trust? Whom do you trust? And if you can't trust the data, okay, if you can't trust the results, how can you think about carrying out a non-linear pushover analysis or a design based on non-linear plastic hinge analysis? Okay, so it is good that people are doing non-linear analysis for their academic purposes, but to come to the real life, okay, we still have a lot of problems. There's still many issues. How do you make sure that the concrete that you have built in a real life at site, how do you ensure the quality of that particular concrete? Okay, even today we don't have uh, any foolproof technique to tell us where are the honeycombing or segregation inside the concrete, unless there is a failure. Then we talk about V greater storm column proportions. That means at any joint in both the vertical planes x, x and y, y, the summation of the moment capacities of the column must be more than at least 20% of the summation of the moment capacity of the gutters. Okay. Sometimes in the latest code they change it to 40%. Okay. And I don't know how many of you are aware, in the draft code of 2016 code, this factor was 1.7. 1.7. That means the moment capacity of the columns should be 70% more than the moment capacity of the girders. You know what happens? If you use that kind of value, even with 40%, the column sizes are very, very large. Okay? And most architects don't accept it. I am in touch with many designers in Delhi NCR region and other parts of the country in your Bangalore side or Bombay side, and there is a complete feedback that architects don't want column sizes to increase that much. Okay, so again, what happens? How do they bypass it? What do they do? They are simply not using this check. Okay, they are not using this check. Again, there is a problem with the compliance of the codal specifications. Okay, and people are building their buildings without this clause. Because if you go into panic mode, and because in panic mode you increase by 1.2, 1.4 or 1.7 as was proposed in the draft, only at the last meeting, just when the code was being finalized, somebody reduced it to 1.4 instead of 1.7. Okay, but even 1.4 is very high. It is very high. Okay, and that is the reason why people don't want to check this and make the columns bulkier, and they lose the workable space. Then this is the specifications corresponding to plastic shearing beams, sway to the right, this is the formula, then sway to the left, minus the plus will change, and so on. And that's how you get 1.25 by 0.87, 1.4 here. Now concluding remarks. There is approximation in the concept of limit state design as per AS456 code. Okay, there is approximation in modeling and analysis of the building. The approximation in computing design earthquake forces as per 1893 code. Okay, we need not be slave to the codes. Therefore, it is all the more necessary to use common sense, good materials, and very good workmanship. This is the key. See, common sense, good materials, good workmanship is what is going to save your building from collapse. Okay. Now I tell you, I visited a lot of buildings in Bhuj, around Bhuj, in almost 100-kilometer radius of Bhuj and Ahmedabad in after the 2001 earthquake. And I found that there are many buildings which did not collapse while the adjoining buildings collapsed. So how do you explain this? That there are two buildings opposite each other. One building collapsed and the other building did not collapse. Most of the new buildings collapsed, and old buildings which are built 20 years ago, 30 years ago, they did not collapse. Okay? It's very baffling that the modern building, latest buildings are collapsing and the old buildings are not collapsing, which are also tall, 6-story, 7-story, 5-story buildings did not collapse, and the new buildings collapsed. Obviously, when we went into the detail, we found that the problem was with the material and workmanship. Okay? And that is the reason why those buildings collapsed. Now, the Indian code writers appear to have a strong belief that the level of seismic hazard in India is same as that in Japan, China, or California and USA. Okay? You understand my point here? I'm saying the Indian code writers, especially after 2002 code, that means this, I'm talking about this 2016 code and the revision which is being proposed now. They feel that the level of earthquake hazard in India is same as in Japan, China, or California. Okay, that's why with each revision, they keep making it more conservative and expensive. How is it possible that the ductile detailing is in seismic zone 3, 4, and 5 are identical when the level of hazard is quite different? See, why do you have zone 3, 4, and 5? Because in zone 3, we are saying that the earthquake hazard level is low, is very low. Zone 4, the level is, the hazard level is a little more. And in zone 5, the earthquake hazard level is even more. Okay? If the earthquake hazard level is different in these three zones, how come that the ductile detailing is same in all three? Okay? In my opinion, the ductile detailing in 3 should be much milder than as compared to 5, and same thing in 4. The question is, where is the evidence? Okay, did we have a single failure of a building in zone 3 due to earthquake? No. There are 7 historical buildings all over the country that are over 500 years old. Okay. There are 7 historical buildings all over the country that are over 500 years old. Has there been any damage to those buildings? If these buildings are standing for the last 500 years, that means we have only mild earthquakes, we do not have strong earthquakes. Same which are seen in California or Japan and China. Okay? So that means there is no need to compare our base years, our activity level with those earthquakes, with those countries. Our code writers are shy to provide logical commentary behind each and every clause. They should give. They are not giving it. The reason? They simply resort to copy, paste, and edit technology. Okay, they copy the cloth from somewhere, one cloth from somewhere, one cloth from somewhere else, and they put it together and edit. Okay, based on their belief. They think this is the way it should be. But there is no evidence to suggest that this is what is happening. Another important thing is that the world is moving towards microzonation. I'm sure most of you are familiar with it. So what is microzonation? It means the seismic. Hello, there's a lot of disturbance. Can somebody mute those mics, please? So the world is moving towards microzonation. It means the seismic map consists of contours of peak ground acceleration rather than arbitrary zones. See, our zones are arbitrary. Even 2016 code, we have seismic zones. How did they decide the boundary of those zones? Do they have? See, there if you look at those codes, those maps, you find that the boundary is very curvilinear. How did they get those contours, that curve? Do they have instruments at those boundaries? The answer is no. They do not have contours on those boundaries. So how did they get such a beautiful curvilinear boundary between different zones? Okay, so that means the zones are drawn arbitrarily. Okay, so the question is, if the country is moving towards microzonation, the world is moving towards microzonations, they have contours of peak ground acceleration, why they are not able to develop similar map for India. Now, if you remember, those who recall this 1962 map of India, there were 7 seismic zones. And gradually, seismic zones from 7 were reduced to 6, then 5, and now 4. Whereas the world is moving towards microzonation, that means more seismic zones, we are reducing the number of seismic zones. Okay, so we are moving in the opposite direction, which doesn't make sense. In order to develop more logical designs, it is strongly recommended that they should develop the peak ground acceleration contours and move towards microzonation of the whole country. In that case, we will be able to come up with more logical earthquake map and more logical design, and it will be easy to follow. Let's hope that one day our Amarinath part 1 will also have contours so that our design becomes more rational and economical. Okay? Advice to my students is they should think about every clause. You should keep on thinking. More you meditate, more you are closer to the truth. Because there are many clauses which are very difficult to understand. Okay? The one possibility of understanding those clauses is that you think, and think. Okay? So structural engineering is akin to yoga, where you keep on meditating till you understand the truth. Okay? Thank you so much.
Yes, sir. Thank you very much for your inspirational, encouraging session. I'm Dr. Ankur Bhogayata, a fellow colleague and working at the Department of Civil Engineering at Marwadi University, sir.
Okay.
Sir, we all are very fortunate to have you with us today, and we would like to take up on a couple of questions raised by the participants over here. So with your kind permission, sir, should we take one by one of them?
Sure. Please go ahead.
Yes, sir. Thanks. Thank you, sir. Sir, we have first question, for performance-based design, how to select different ground motions? That is a first question. For performance-based design, how should we select the different ground motions?
See, that's what I discussed in my presentation. Right. That currently we have hundreds of ground motions, but only in Northeast India and North India, that means in the Himalayas.
Right.
And those are very, very mild earthquakes. See, the peak ground acceleration may be hardly 0.1 G or 0.15 G.
Right, sir.
So right now we do not have any strong earthquake recorded anywhere in India, including Bhuj earthquake. Okay, and there was a problem, serious problem with the Koina earthquake. I don't know how many of you have your family with the Koina earthquake, which occurred in 1967. They do have some kind of time history analysis, time history record of that earthquake. But if you look at the original paper, it is mentioned that there was a problem with the machine during the earthquake, and for almost 10 seconds, nothing could be recorded.
Okay.
They have the starting point of the acceleration, the last part, not the middle part. That is bogus. It's a very stupid argument. The fact remains, you don't have earthquake, you didn't have a machine, but because of political reasons, you didn't want to accept that. See, government will ask questions. They will ask accountability. That we have given you so many millions of rupees. You imported the equipment and you said you have installed it. Why it was not working?
True, sir. Right, sir.
So my answer to the question is, let us not talk about performance-based design as on today.
Got it, sir. Right.
Okay, see, academics are interested in doing research. They want to publish papers. Fine. Let them publish papers.
Right, sir.
Okay, but let us not, please don't ruin our buildings.
True, sir. Okay, sir. Sir, the next question. It is inevitable to stop hinge formation at column base. It is inevitable to stop hinge formation at column base. Will it not result in total collapse of structure?
See, we have to understand the earthquake. How is it occurring? See, earthquake is a ground motion which is going to occur laterally for a few seconds. Right? It may be, it keeps on cycling back and forth. Okay, and the magnitude keep on changing. As if you remember, let me see. Can you see my slide? Can you see my screen, please?
Yes, sir, it is visible, sir.
Okay, so what I'm showing here is this. You have to understand what is the meaning of, physical meaning of this particular diagram. See, this is your acceleration 0.1 g, 0.2 g, 0.3 g, 0.4 g, and this is minus 0.1 g, minus 0.2 g, minus 3 g. This is time in seconds. So what is happening? Plus and minus means left and right. If your building is standing in the without an earthquake, it is standing in a vertical position. Now, when you push the building to one side, say towards right, okay, that is positive, and when you push the building reverse towards left, that is negative. So here, sorry. So what it shows here is that this building is going towards left, and here the building is going towards right. Left, right, left, right, left, right. Okay? So building is vibrating left and right of its mean position. Okay? So what happens that at this position, say, there is a formation of a hinge at the bottom of the column. But immediately the earthquake reverses the direction, it goes back to zero. When the earthquake reverses the direction, goes back to zero, that plastic hinge which formed here at the bottom of the column, that will disappear. Now the building goes in the right, and again it goes to the maximum position, and here again hinge may form at the same location, or maybe in a different location, but in the opposite direction. Okay, suppose here the hinge was hogging, here the hinge may become sagging. Okay, again immediately there is a reversal of the earthquake force, and the earthquake force reduces to zero. So that hinge which formed momentarily is now released. So what happens that at every such peak, the hinge forms and immediately it is released because there is a change of the direction of the earthquake force. So I hope now my point is, I made my point clear, that if there is a formation of plastic hinge at the bottom of a column, it does not necessarily mean that the building is going to collapse. Because immediately the direction of the explosive force will reverse and it will unload. When it unloads, the hinge will disappear. It may leave some damage to concrete. It's possible, yes. Okay, but then the earthquake does not follow the same peak every time. The peak keeps on decreasing. So it's possible that at one particular location, a hinge has formed momentarily, some concrete has damaged, or the reinforcement has yielded, but then it disappears. It becomes elastic again. Next time, the hinge may form somewhere else.
Right, sir.
Okay, so the bottom line is, don't worry about the formation of plastic hinges at different locations. Okay, because the earthquake force is dynamic. And it lasts only 10 seconds, 20 seconds. You have this earthquake which is 30 seconds. In fact, it was recorded up to 120 seconds. But the first 10 seconds, in fact, from 3 seconds to 6 seconds is the most strong part.
Right, sir.
Okay, and nothing is going to happen in these 5 seconds, provided the quality of the material is good, the workmanship is good. Okay.
Right, sir. All right, sir. So the next question is on regarding the software. That generally commercially available software consider accidental eccentricities easily, but is it possible to input or to enter the dynamic amplification factor that's around 1.5 in commercial available softwares? Is it possible?
No, it is not possible. Okay. Now let me try to answer this question. See, when the code was being revised in 2000, 2001, 2002,
right.
At that time, Dr. Arya, A.S. Arya,
yes,
who expired last year.
Right, sir. Right.
Okay, he was the chairman, and he somehow came up with that equation, or the committee came with that equation, 1.5e plus minus 0.05b. Okay. At that time also I was in the committee and I strongly recommended, please do not include this factor 1.5 because it is not possible to incorporate in the softwares. Okay. Right. And once it is not in software, it will not be implemented inside. At that time, he said, no, our engineers will do it, or software will modify the software and they will include this factor 1.5. Okay. Right. Now what happened, even after several years, that was not modified, software was not modified. So finally, if you recall, they issued an amendment. Right. And in that amendment, they said that if you're carrying out dynamic analysis, that is a response spectrum analysis, then treat this factor 1.5 as 1. Right, sir. Do you remember that clause? Yes, sir. Okay, so they came back to E plus minus 0.05b. And because you're carrying out dynamic analysis, therefore E is automatically taken care of in the Stevens matrix. Okay. So what I'm trying to tell you to answer your question, that as far as eccentricity is concerned, the earthquake code, the software do not calculate E explicitly in the software. Okay, sir. Right. They don't calculate. So what they say, the formulation of Stevens matrix itself takes care of E. Therefore, now the software only has to account for accidental eccentricity, which is 0.05b or some other value. Right, sir. Okay. Okay, sir. And this time again in 2016 code, they brought back the old one. They removed the factor 1. They think that they can dictate terms to the software companies. The answer is no. But the problem is, it is almost very difficult to calculate the eccentricity. Right, sir. Okay. True, sir. So the next question, what is the effect of mass asymmetry on building with flexible or semi-rigid diaphragm?
So the question is regarding effect of mass asymmetry on a building with a flexible or semi-rigid diaphragm.
If you uh, see my discussion, which I mentioned about this one, okay. So here is the center of mass, here is the center of rigidity. Okay, this is the actual as per your calculation, what is center of rigidity, and here is the center of mass. This center of rigidity, the center of mass. Okay, now whether the mass is, you have mass eccentricity, or you have uneven mass distribution, or you have flexible diaphragm, doesn't matter. Effectively, you have to calculate what is the center of mass on a given floor and what is the center of rigidity on the given floor. Okay, so whatever may be the cause, whatever may be the cause of this irregularity, ultimately you need to calculate the location of center of mass and center of rigidity, and then you use those two equations, EDA and EDV, okay, which I told you. This is actual center of mass and this is the modified center of mass because of this equation EDA. So EDA is basically the distance between CM prime and CR. This is EDA. CR remains constant. CR doesn't change. Okay? It is only the CM which is changing because of this equation. This is EDA and this is EDV. So CR remains where it was originally. Because CR is the center of rigidity of the building which does not change, which cannot change. It's only the apparent mass which is changing. Okay, so whether it is the mass eccentricity or flexible diaphragm, the basic torsion remains same. So here, ultimately, this is your CM, this is your CR, this is the reaction offered by the building, this is the force offered by the earthquake, and the distance between this and for equilibrium, this force has to be equal to the reaction. Okay, so the distance between force and reaction, this eccentricity is going to cause torsion. Okay, so ultimately it will lead to torsion, and chances are that concrete will not be able to sustain this deformation at the flexible end in the columns or in the beams, and therefore concrete will simply fail. Okay.
Right, sir. True, sir. Sir, the another question we'll take up, that is, kindly tell about the acceptance criteria in performance-based design for seismically isolated RC buildings. So, acceptance criteria in performance-based design for seismically isolated RC buildings.
See, the point is that if you have seismically isolated it, that means you have carried out base isolation, right? How did you isolate? By base isolated? Hello?
Yes, sir. It means like that only.
So once it is base isolated, you don't have to worry. The building is safe, no matter what. That's the whole purpose of base isolation. Once you have isolated at the base level, no matter what is the earthquake, your building is always safe. It is always elastic. So, as far as this performance base is concerned, it's only to ensure that the base remains isolated. If you put, for example, if you put the whole building on wheels, fine, matter ends. There is a question of anything happening to the building. Building is absolutely elastic and safe, guaranteed. Is it okay?
Yes, sir. Yes, sir. Sir, next question, Ankur, sir.
What happened?
Sir, just a minute. I'll.
Okay, please take your time.
Sir, for next question, for basement structure, many foreign codes deal with the shear wave velocity. Why IS code does deal with that?
Doesn't deal with this. See, as I said, our code is based on copy and paste technology. We are not doing any original research. No IIT is doing any original research. So whatever is, whosoever is the controlling the codal committee, he comes up with his own specifications. He doesn't listen to anybody else. He just decides, okay, I will put this, I will put this, I will not put this, I will not put this, and that's how the code is framed. So you have to ask this question to the people who are framing the code. Why they removed DBE and MCE? See, they didn't change the base shear formula, right?
Yes, sir.
The base shear formula still remains the same as before. Now, see, since you are in the teaching, how do you explain to the students what is Z by 2? Do you get my point?
Yes, sir. Yes, sir.
See, in order to explain to the students what is Z by 2, see here this Z by 2. You tell them that Z is coming from the spectral acceleration given in the code corresponds to MCE. And when you divide by 2, you get DBE. And further, if you divide by R, okay, then you get the design spectra, design base shear. Okay, and if you delete the term DBE and MCE, you can delete the term, but how do you delete the concept? This concept is coming from there only. And when you look at any international code, whether it is ASC code or Euro code, they are using those terms. In fact, they are using those terms with probability. Okay, DB is still 10% probability of being actually in 50 years. That is how DB is being defined even in Eurocode EC8. And MC is defined as 10% in 100 years. That's how MC is defined in Eurocode, even in ASC code, ASC7. So those people are using the same definition even today, and they will continue to use. What is the logic for deleting in our code? And remember, these definitions were deleted in the last meeting when the code was finalized. It was not deleted during the previous meetings in which there were a lot of discussions over the last 3-4 years. So suddenly somebody got a wave, maybe shear wave, I don't know, to delete those terms, and those were deleted. Similarly, minor earthquake, moderate earthquake, and strong earthquake, these terms were also deleted. The entire preface, which was about 8 pages or 9 pages, now is only 1 page preface. There is no justification in my opinion. Okay, if somebody reads the preface of the earlier code, that is 2002 code, he gets an idea of what is earthquake, how the code intends to solve this problem. But not anymore, because they have removed the entire preface, they have removed these basic terms.
Yes, sir. Yes, sir. Yes, sir. So the next question is related to retrofitting, that how to implement this confinement reinforcement tie links in existing building to increase the ductility, since the ductile detailing as per 13920 is applicable for the new construction only. So how to implement, that is what is this question.
See, it is, see, you have to understand what is the level of people in the field. Okay. you find, at least I find very difficult to find good uh, mechanics, good masons to do a RCC building seriously with quality control. Now you're talking about retrofitting an old building.
Yes.
Okay. Now retrofitting job is a highly specialized job, and you need a lot of patience, a lot of experience to do the retrofitting of the old buildings, especially when you talk about ductility.
Yes, sir. So sometimes it may happen that rather to improve the strength because of the efficiency of the labor, the structure may get damaged also.
Very badly damaged. Very badly
Yes.
damaged.
Yes, sir.
I tell you, about 20 years ago, I was helping the Kendriya Vidyalayas. You have Kendriya Vidyalaya in every city, or most of the cities in the country,
Yes.
central schools. And they wanted a review of their school buildings in many parts of the country to do seismic retrofitting.
Right.
I visited about 8-10 buildings in different parts of the country, north, south, middle, including Gujarat. And I gave them a very categorical recommendation that please don't touch these buildings. They're designed, they are built very nicely. If you touch them, you may damage them.
Yes.
Okay. I remember I visited a building in Bhuj. There were two Kendriya Vidyalayas. I don't know how many of you are familiar with Bhuj city.
Yeah.
There are two Kendriya Vidyalayas, one for the Air Force, other for the Army. And Air Force building was, after this Bhuj earthquake, they wanted to retrofit it. And the recommendation for the building was nothing is to be done, just plaster it and continue with it. No retrofitting is required whatsoever, because no damage has occurred to this Air Force building. It was a two-story building.
Right.
Now something very interesting happened with the other building, which was just about 1 or 2 kilometers away from this Air Force building. And in that building, there was an expert from one very leading CSIR lab. And as soon as he entered the building, he said, no, the building has to be demolished. It is in very bad shape. And when he came out, he's given writing that the building has to be demolished. Okay.
Yeah.
Then they appointed another. Now, what happened? The school teachers. And it was a school from class 1 to class 12.
Right.
So the school teacher said, sir, we don't think there's any damage to the building. Only the plaster has fallen. And they were using these masonry blocks. The entire building was only masonry blocks. They said that these masonry blocks have damaged, and we are confident that we can teach inside the building. The building is safe. And the building need not be demolished. They sent a representation to headquarters in Delhi. Can you believe those teachers of primary school or Kendriya Vidyalaya who were just school teachers, and they made a representation that we don't think the building needs to be demolished. I mean, they are putting their own life at risk.
Yes. Otherwise, non-technical people will have more hesitation about
Exactly.
occupying them.
Exactly. And they said, no, we don't agree with it. And so what the headquarters said, no, you do not enter the building. And they provided tents. And tents were installed, on the ground of the school. And the classes were held inside the tent every day. Nobody could enter the building. It was out of bounds.
Yeah.
They appointed another committee, unfortunately from Roorkee University, from IIT Roorkee. And the two experts visited the site, one from earthquake department, one from civil department, my senior. And they gave a very, goal report that, yeah, the building can be retrofitted, but it is better that it is demolished because it's going to be very expensive. So again, the teachers were very angry.
Yeah.
How is it possible? We are saying the building is safe, and the adjoining building of Kendriya Vidyalaya, this Air Force building, was much better condition than, no, much worse condition than ours.
Hmm.
And that is working, and why ours is not working? They again made a representation. No, we don't agree with this. Now the chairman of the Kendriya Vidyalaya, he was an IS officer, he was in trouble. What do I do? First report came from CBRI Roorkee, which is CSIR lab. They said the building has to be demolished. Now head civil IIT Roorkee and head after development IIT Roorkee both give the recommendation that the building has to be demolished because retrofitting is very expensive, very time consuming. Now how do you supersede these two recommendations? See, government development works on paperwork.
Yes.
And in paper, there are two reports, independent reports by three experts saying that building has to be demolished. Who on the earth can say no, building is not to be demolished? And you are in any case, you are school teachers.
Yes.
How can you say that? Now what happened? I hope I'm not taking too much time.
No, sir, it's okay. Your experience that gives us lots of guidance. There are so many questions actually.
Yeah, so because this is a very eye-opening situation of the country for so-called
Yes.
experts.
Yes, sir.
So what happened that the executive engineer, there was only one executive engineer for the entire Kendriya Vidyalaya Sangathan in those days, and he happened to be my friend, my senior, and while I was a student from Roorkee University itself. Then finally he talked to somebody and he said that I'm in trouble, what to do? So somebody suggested him to come to me. He came to me and he apologized that I should have come to you first in the first place, and somehow because of my boss he said go to head of development only, and I went to head of development and he said I'm the expert, and so he came and he gave this recommendation. Now I'm in serious trouble. My boss is also in serious trouble because now we have got two reports by three experts saying the building has to be demolished. But the school teachers are not convinced. Now my problem is very simple. I can't take you officially. Because the government has already spent money on two experts for two different organizations. Now on what basis we say that we are taking third expert, and so if third expert gives a different report, then do we go to the fourth expert? Right?
Right.
That means you are trying to manipulate the results. You want an expert who will say the building is safe. So our problem is we can't do that.
Yes.
Now you please tell us what is the solution. I said, okay, let me go there first. So I was taken on a different project. They couldn't take me on this particular project, and they could not take me through Kendriya Vidyalaya.
Yeah.
Okay. Obviously, they could not take me from there. So they asked somebody else to, engage me for some other building in Bhuj. And then I went there, stayed 2-3 days, and did the testing myself. I tested various columns. I spent several hours on 2 different days on that building, and I got the removed. They said that the columns are unsafe, beams are unsafe, and so on. I found that there were cracks in all the beams, all the columns at the level of construction joint. See, there were two construction joints in the middle of the column, at 1 meter height, another 2 meter height. In between, it was all right. I got the plaster removed, and there was no crack inside.
Okay.
The crack was only in the plaster. And those people, they saw the crack in the column, they said, no, columns are gone. Whereas the crack was only in the plaster. And that was at the level of construction joint, which was visible. Okay. Similarly, in the beams. In the beam, there was no crack whatsoever. The crack only in the plaster. And the plaster was at few places 50 mm thick. 50.
Oh my God.
In column as well as beam both. Okay. So I got the column removed, plaster removed from many buildings, many classrooms, and I checked it, and I said that look, here is the building. I tested that concrete. It was coming out to be M20, M25. and I said, now the building is safe. So I made a presentation to the chairman of the Kendriya Vidyalaya. He was convinced that I spent so much time because he knew that the other experts hardly spent any time, maybe more than hardly. The first expert spent only 10 minutes. The second team spent another 1 hour or 2 hours only. And he knew that I spent 2 days inside the building.
Yes.
Okay. So finally they accepted my recommendation. And I was thankful to those non-technical teachers that they had a very strong conviction that we think the building is absolutely safe and we should move to the building. That was amazing, absolutely amazing and incredible.
So one should be able to talk with the structures actually. So
yeah, you have to feel the pulse of the structure, and as I said, common sense is the must.
Yes. So it was really, sir, nice experience that you have shared, and this thing will give us the insight also that whenever we are dealing with the structures, specifically in retrofitting, how we should move forward. Thorough investigation is required actually.
See, I tell you another thing, that I went to this building recently, just in 2 months back. Yeah. In Silvassa. Okay. And there was, still that building is, they want to retrofit the whole building. Okay. The problem is that in some of the blocks, the concrete has gone at least 5 and 10 centimeters inside the core. And it's such a heavy building, heavy loaded building. The retrofitting is just not possible in some of the blocks. They have no option but to pull them down. Okay. So point is, retrofitting is not possible every time. The owner may insist, no, I want to retrofit it. It's just not possible. So you have to be careful. You have to be clear that as far as my understanding is, my common sense says, it can be retrofitted or it cannot be retrofitted. Okay. You can't yield to the pressure.
Yes.
So please give a recommendation that, it can be done or it cannot be done. That's not the way to work. It is not a professional work.
Yes. Yes, sir. Sir, the next question that we have is, the response reduction factor affected by regularity or irregularity or not?
No. Response reduction factor is something different altogether.
Yes.
Okay. Unfortunately, in our code, R factor is totally arbitrary. They have chosen arbitrarily. When you say factor 3, 3.5, 4, 4.5, or 5, a purely arbitrary number. There is no logic behind it. Okay. But as far as the R factor is concerned, theoretically, you are supposed to carry out a nonlinear analysis. Okay. With that kind of nonlinear behavior of the building. Okay. And then develop what is R factor. So R factor is not a function of this irregularity, but it is a function of, in fact I mentioned it.
Yes, the overstrength, ductility.
Overstrength, redundancy, and ductility. These are 3 factors which depend R.
Yes. Okay, sir. The next question is, which design method generally we should follow practically? It's so whenever the newcomer starts designing, the methodology that they should follow. So as you mentioned that by the time as you go deeper and deeper, and you will come closer to your exit analysis. So one has to start with linear and then.
See, for all our practical purposes, whether it is a 5-story building or a 10-story building or a 20-story building, your linear analysis response spectrum method gives you a fairly reasonable result. Okay. If you can ensure that your building is regular, because see, I told you why I'm not in favor of a torsional behavior, why I don't want irregularity. I explained to you already in these slides. This is the reason. Okay? At this corner, there is going to be a column, right? And the column will be stretched because the building is rotating about the vertical axis. Okay? The question is, can your concrete on the column undergo this additional strength? Okay? So once it exceeds 0.35%, your column is gone, concrete is gone. So, see, one thing you have to understand, when we are talking about irregularity, what is we are looking at? We are not looking at the magnitude of the torsional force. Unfortunately, when you are carrying out this analysis,
right,
when you are looking at this eccentricity, you are looking at the force, torsional force. Okay, torsional force is not important. What is important is the torsional deformation. Okay, what is important is the torsional deformation, not the force. What I talked to a couple of designers, what they say, sir, this increase in the torsional force is coming out to 10%, I will increase it 20%. Okay, now my building is safe and I can go for a unsymmetric irregular building. The answer is no. We are not looking at, we should not be looking at the force. Although our design method happens to be force based. We are calculating the force, multiplying by E, getting the torsion.
Yes.
We are looking at the force, but we should be looking at the deformation, not the force. And if you look at the deformation, the question is, can your column concrete or beam concrete take this additional strength beyond 0.35%? The answer is no, it can't take. And that is the reason in all buildings that have collapsed, even in Bhuj earthquake or in Ahmedabad, the failure was due to torsion, not due to any other reason. Okay?
Yes.
So that way, elastic analysis, response spectrum analysis, forget about push-on analysis, forget about performance-based design. Okay, those are good for research, for publishing papers. But as far as the real building is concerned, go for a linear elastic response spectrum analysis, carry out seriously and make sure that your building is symmetric and it is regular building. That's it.
Yes, sir.
And make sure the quality of material and workmanship is highest possible standards. Because I told you, I showed you that building of 1964, earthquake in somewhere in Argentina or where. Okay? That ductility I showed you, that failure of the ductility. And that was done in M15 concrete. I'm talking about this figure. This was done back in 1960.
Yes.
The building was built in 50s. Okay, and at that time there was no plastification, no nonlinear analysis, no time scale analysis, no code even. Our Indian code came in 1962 and the building collapsed in 1964. Okay, so these are pure common sense. You look at the deformation. Deformation is visible. So if those people can do this kind of wonders in those days, why can't we do it today with so much resources available to us?
We are just creating unnecessary complexities in the structure.
Yeah, they want to bring in, they want to, see, let me talk about one more thing. Yeah. We're talking here about code of practice. What is the title of the code? It says code of practice or in earthquake resistant design. What is the code? It is code of practice. So whatever is being practiced in the field should be codified. Okay, you should codify the code of the field practices and put it in a code. Not bring your research from your lab or your computers into the field. See what is happening?
Yes.
And everybody is facing the music.
Yes, sir. The next question that we have is we talk about plastic hinge, but three plastic hinge formation leads to failure. Why we not design the structures which has only least possible rotation?
No, that's what I'm saying. That it is not in your hands.
Yes.
I showed you this slide in the beginning itself.
Hmm.
This one.
Hmm.
See, this slide shows you hinging at different locations at different times.
Hmm.
Okay. The way the plastic hinge will form depends on the moment capacity
Hmm.
of the particular section. And moment capacity will depend on the bending moment and the reinforcement, the quality concrete, the amount of reinforcement, and so on.
Hmm.
The hinge is forming at different locations at different times,
Hmm.
which is not in your hand. The building has been built.
Yes, sir.
So the certain material has been used, certain workmanship has been used, a certain level of workmanship has gone in the reinforcement preparation
Hmm.
and compaction, curing, and so on.
Hmm.
So what I'm saying is, unless you know how to measure that quality of concrete in every location, how can you control the or forecast the formation of the plastic hinge? You can't,
Hmm.
right? And that's what I'm saying. Forget about performance-based design. Forget about push-on laces. It is good. See, I have been doing push-on laces or non-linear dynamic time steel laces for the last 40 years.
Hmm.
In fact, 45 years.
Hmm.
Okay? And that's why I'm saying forget about those things. It's good for research.
Hmm.
It's not going to take you anywhere as far as the field is concerned.
Yes, sir. Sir, what are your views related to behavior of pre-stressed concrete structures under seismic conditions?
See, as far as the pieces of concrete structures are concerned, as long as the structure remains in the limit state of serviceability, it is good.
Hmm.
But the moment it enters into the limit state of collapse,
Hmm.
then pre-stressing is gone.
Hmm.
Why it will collapse? It will go collapse because hinges formed, and once hinges formed, the pre-stress will go.
Hmm.
It behaves as an RCC structure.
Hmm.
So, whatever is the consequence of RCC structure, same thing happens here.
Hmm.
That's why when we design a pre-stress building, a pre-stress beam, we design it for limit state of serviceability, not collapse.
Hmm.
Because we're only checking it.
Hmm.
Okay.
Sir, some of the key points related to expansion joint in earthquake resistant design. That during design, what care we have to take related to this expansion joint?
See, all you have to make sure is that when the building vibrates, it depends whether the building is isolated, because this expansion joint, that means there are two blocks at least, and they may vibrate in two opposite modes. One is vibrating towards right, other is vibrating towards left. Okay, so they should not hit each other. They should not impound each other. So the gap between the two blocks has to be sufficient so that they don't hit each other. They don't impact each other. Okay. See, some of you may wish to refer my book on dynamics, where these things are explained. My book on dynamics and structures, which is available on Amazon. So, if I don't know how many of you heard about it, about that book or not. Have you heard about that book before? No.
Yes, sir. Yes.
Okay. So, I think if you refer that book, that gives you fairly good detail about this expansion joint and so on.
Okay.
And how to carry out these dynamic analysis, the static analysis, how to manual analysis, and push-over analysis, and PBD. Performance-based design is also explained in that book.
Okay, nice. Sir, next question is, it is generally recommended that UTS versus YS ratio of means ultra strength to yield strength ratio of rebar should be minimum 1.25. Wouldn't be that lead to a higher probable moment capacity, since the 1.4 factor also takes over strength of 1.25 into account?
The thing is that if you look at the stress and curve of steel, you have a yield point and then the ultimate strain. And there is a rise in the ultimate, the failure force as compared to the yield force. Okay, that is there in any case. So what they have done is, see what is happening in India. There are a lot of local steel companies who use scrap, local steel scrap or iron scrap, and mill and prepare steel, which is much cheaper. And that's what was used by most of the buildings in Ahmedabad and Bhuj.
Yes.
Okay. So, in order to ensure quality control, they specified that the minimum level of these two forces has to be 25%. So that they don't use local material, there is proper quality control in the construction of steel, reinforcement, and then so that the building will behave properly. So this factor 1.4, which is there in the code, accounts for this factor 1.25 divided by 0.87.
Right.
Okay.
Sir, in next question, if you have Y-shaped building, then which direction shall be considered as principal direction in response spectrum method?
None.
Yeah, none. Okay. The next is the use of response reduction factor 5 without adherence to provision of 13920 is justified or not?
You mean to say you want to use factor of 5, but you don't want to do the data detailing?
Adherence to the provision of 13920, is it justifying?
So that's what I'm saying.
Yeah.
What is your intention? Your intention is to use a factor of 5, but not follow the data requirement. Is this what you're saying?
Yes, they mean to say like that only.
See, as I mentioned during my whole presentation, I am not happy with 193 as well as 13920. There's a basic flaw with both the codes. Okay? And the flaw remains that in 13920, they are providing same level of ductility, unless that ductility 13920 was applicable only in zone 4 and 5, not in 3. And later on, in 2002, they introduced that zone 3 also and made it compulsory zone 3 also, which was not required. There is absolutely no requirement, in my opinion, in zone 3. Okay.
Yes.
Then my second objection is to the zoning itself. How do you define zone 4? How do you define these boundary conditions? Let me show you what I'm trying to say. Here. See, how do you get these beautiful curves? How? You get these beautiful curves here. You get beautiful curves here. How do you get these beautiful curves? I want to know this.
Yes.
These beautiful curves here like a fish. Like there's a duck here, and there's another duck here. They are talking to each other. How do you get these beautiful curves here like this? How? Do they have accelerometers installed at the whole periphery of these curves? The answer is no. They don't have. If they don't have instruments installed along the whole periphery, how do you get such beautiful curves? I want to know this. Okay? So these are all arbitrary.
Yes.
So why, I mean, if somebody is on the boundary,
Hmm.
somebody is on the boundary here.
Hmm.
I remember there was a collapse of a TV tower at a boundary of a zone, wind zone between 4 and 5.
Hmm.
There was a dispute. The designer took the smaller value, not the higher value because it was at the boundary.
Hmm.
Now there was a dispute. He said, no, because at the boundary I will take the smaller value. The
Right.
point is that these codes are totally arbitrary.
Hmm.
Somebody is taking it as something, it is sacrosanct.
Hmm.
It is not sacrosanct.
Hmm.
Okay? You are making it too complicated. For example, earlier, if earlier building in 15 concrete, like for example, there are water tanks in Bhuj or in Gujarat, which were built, let's say, maybe in 1950s, 1960s,
Hmm.
and they're still working today.
Hmm.
Is it not? There are water tanks in Gujarat state which were built 50 years ago
Hmm.
or 60 years ago. They were built in M15 concrete or M20 concrete at the most, using mild steel.
Hmm.
And nothing happened to those water tanks if they were maintained properly.
Yes.
Okay, so why you want to make it M35
Hmm.
with such a heavy reinforcement now? What for?
Yes.
Same thing is happening to our buildings.
Hmm.
Unnecessarily, you are increasing the level of reinforcement, ductility reinforcement, and so much ductility reinforcement in the zones, in the beam column joints,
Hmm.
that you can't even pour the concrete.
Yes.
So what is happening?
And on the contrary, life of the structures gets reduced compared to older structures.
That's right. Yeah, it will reduce.
Yes. Sir, one research scholar is there in the audience. He is asking if we use older version of IS codes 1893 and 13920, even after the newer version of codes were published in 2016 with draft version of floated even earlier. Is it valid for PhD work for any consequences?
No. As far as PhD work is concerned, you are free to do whatever you want to do.
Hmm.
Okay. All you have to say in your thesis that you have used this clause from this particular version and give a justification why you have used that clause.
Hmm.
Why do you think this clause was used?
Hmm.
Okay. It has got nothing to do with your legal requirement of the code provisions.
Yes.
You can use 1962 code. Why not?
They have to quote version also. That's it.
Yeah, they have to quote the requirement. They have to specify that I took this clause from so and so code, and my intention behind this is this. Because in research, you have to justify why you have done this.
Yes.
Okay, so as long as you justify, I did this because of this reason, fine. Go ahead. Go ahead.
So, two last question. Why we are equating base shear in seismic coefficient method and RSA? I think question, why we are equating base shear in seismic coefficient method and RSA?
No, see, the thing is that you have a building you have a given building, and you have option to calculate the earthquake force using seismic coefficient method or response factor method, right? Now, earlier in the 1984 edition of the code, you could calculate the seismic coefficient method base shear, which was very high, which was almost 4 times the base shear that you will calculate using response factor method. Okay. In the 1984 earthquake code, if you use the seismic coefficient method to calculate the base shear, that base shear was as much as 4 times of the base shear that you calculate using the response factor method. And I did ask this question Dr. Chandrasekharan and Dr. Arya in earthquake development in those days. I said, why you have done this? Why there is difference of 4 times? And the answer was that we want to give incentive to a person who is doing dynamic analysis. Because in 80s, carrying out dynamic analysis was a very big thing. There were no computers, no software. You have to develop your own algorithm on, and there were no calculators also in those days. You have to do a Holzer method manually to get the frequency and mode shapes. Okay. So in those days, the intention was that you carry out this nonlinear analysis or the dynamic analysis, response spectrum analysis manually, and because the efforts are so much in doing this analysis, so we give you incentive that okay, if you do it, you end up in saving lateral force. The building becomes economical. Okay, that's why we are recording it. But then later on, because there were disputes, because the factor of 4 or 3 is very high. So in 2002 edition, they were made equal. That your base share remains equal. Only thing is your distribution along the height will change, depending upon whether you are using the elastic method, or static method, or you are using the dynamic method. That was the only difference. Okay. So code has evolved over the years. Okay, and that is the reason for it.
And so last question, how to perform torsional analysis of hill slope buildings?
I have discussed that quite in detail in my book. You have to carry out response spectrum analysis. Okay, 3D response spectrum analysis, modeling has to be done. Then you carry out your analysis, and I have told how to carry out the torsion analysis, how to combine the forces. It's all given in my book on dynamical structures.
Yes. So I think we have tried to give answer of almost all the questions. 2 to 3 repeat questions that we have ignored. Otherwise, even though we were having intention to take maximum benefit of sir's experience, so actually session is over at 1:15, but it has crossed more than half an hour. So that is the runtime questions. They were coming because of your soft answers. So on behalf of Marwadi Education Foundation and Atal Academy, we are very much thankful. And even we have got lots of response in the chat from the participants also. They are very much happy with the way you have explained fundamentally, sir. So, sir, thank you very much.
Thank you very much. I'm really happy with these so many questions coming from the audience.
Yes, sir.
And I hope they were able to gain something out of it.
Yes, sir. Yes, sir.
Okay.
Okay,
so
sir.
It was my pleasure and all the best. Thank you.
Thank you very much, sir. We'll be in touch with you continuously.
Sure. Most welcome.
Yes, sir. Okay. Thank you. So participants, we with this we end the session here, and the next session we will start 15 minutes late, and that will start at 2:30. Yeah. Thank you, sir. So with this we end the meeting, sir.